So welcome to the pre-recording of lecture 6 of MCS 260 in this 8-week summer session. This is the second part of our third session, so it's essentially not lecture 6 as far as the number of the session, but we are still within the first week of classes. In this first part of the lecture, I will talk about formal languages, and then we will go into the composite data types of Python. We can already write a very interesting small Python scripts, but we can solve a lot of problems if we know the basic data types that Python offers. So I talked about control structures earlier on. Many programming languages start very early on with loops and conditional statements. In Python, it may make sense to first focus on the composite data types before we get into the loops and the if statements, the conditional expressions. Formal languages. So we distinguish when in any language, also in natural language, we distinguish between syntax and semantics. Languages are typically classified into generations. So there is the machine language, it's just a sequence of zeros and ones. Assembly language provides you with shortcuts for the for the instructions. So as a programmer, you can read assembler programs. Then there are the high-level programming languages. The early examples are Fortran. Fortran is a formula translator, and our first programs actually are starting from formulas. So Fortran is one of the origins for the application areas, scientific applications. Business applications, we have COBOL, and then there is the C language, which is more tied to the Unix operating system. So these are the earlier examples. And in some sense, languages that follow after that, the Ada, C++, they are object-oriented languages. And many other languages are actually object-oriented. Python is a framework language. A little bit more ambitious name would be a problem-solving environment. But perhaps let me not go into this. So in a framework language, you have the entire environment. So there are the extensions of the language, which are the modules and the packages. So Python has its core, and then there are the modules. Modules and that are often that in previous generations of languages would not be considered as part of the language, more as the environment that surrounds the language. So Python comes with batteries included. So in the last lecture or the first part of this session, we introduced Turtle Graphics. Turtle Graphics is a module that is standard delivered with Python. Although it's a little bit far from an actual conventional high-level programming language. We distinguish between natural languages and formal languages. In some sense, there is the context-free grammar. So that's another way in which you can distinguish a formal language from a natural language. Going back to the first lecture, what computer science does is the study of algorithms. And an algorithm is an ordered set of ambiguous, unambiguous, executable steps that terminate. So the unambiguous is important here. What separates a formal programming language from a natural language is that you have only one way in which the language can be understood. So that makes it very clear. Um, um, a lot of problems occur in the natural world when languages and sentences can be interpreted in many other ways. Programming languages are to be interpreted in only one way, not as natural languages. So keep that in mind. There is the syntax and there is the semantics. Syntax is what properly belongs to the language, which is a valid statement. Semantics refers to the meaning of the sentences. I will give an example. Um, let me explain it in terms of the assignment. So the assignment is assigning a value to a variable. When you think about the syntax, you have an operator, which is the equal, which is, in my opinion, not a good symbol, but it stocks, and in some sense, Python has inherited this from C. So you have an operator, you have an operand left, the name of the variable. At the right, you have a value or in general an expression. So that is the syntax. So this is saying the appearance. So you expect that an assignment in the middle there is an equal symbol. You have a name of a variable. So you cannot have a value. You cannot write 3 equals 2 or 2 equals 2. So both are actually wrong. Um, so that would be an invalid syntax. So at the left there should be a variable. Um, at the right there should be either another variable or which can be then more general, an expression that that involves variables. But again, what is at the right should be executable, and that goes to the semantics. So what does the assignment do? It actually evaluates what is at the right and it assigns it to the variable at the left. So if you have a variable that for which there is no memory allocated, for example, if you think about a composite data structure in more a lower level sense, then you have a semantic problem, not a syntax problem. If you cannot evaluate the right side of the expression, even if it looks all perfectly fine, then you also have a syntax error. Um, the Backus-Nauer form is a formal notation to define a programming language. Now, it is named after two Turing Award winners. So I mentioned the Turing Award in a previous lecture. So one way to look at this course also would be to look at the Turing Awards. So I I always learn when I teach this course. So when I did a Google search, I downloaded the paper that was cited more than 4,000 times, the 1977 Turing Award lecture of John Backus, where he explains functional programming as a way to get away from the von Neumann machine model. So Python is a flexible language. Uh, we can program in a way that is completely making abstractions from the physical von Neumann machine, the model that is used to is much closer to the machine. The Backus-Nauer form is important to describe a formalism of a language. And this could be useful if you want to define a specific input format, what the users to your program needs to be defined. I cannot in this introductory language explain what is the complete Backus-Nauer form, would also do injustice to an enormous accomplishment that deserved the Turing Award. But I can explain the formalism. So every language consists of an alphabet and some rules that depart from an axiom. So we can, for example, describe what is a sum of natural numbers. I have to define what is a natural number. So a natural number is either a digit, 0 up to 9, or it is a sequence of digits. So we have these vertical bars, which is the bar that I used in the previous lecture to demonstrate the pipe. But here it means simply an OR. So we have one of the digits. So if you read the slide, it starts from the axiom. And then what is a sum? A sum is a plus, and it starts with a number or another sum. So the sums can are consisting of sequences of numbers plus and then another sum. So a sum is not restricted to one plus. You can see the recursive nature of this. So you can replace a number by a sequence of digits. A sum can be then again represented by a number plus another sum. And a sum is either a number or it is a number plus a sum. So perhaps I'm muddling this up. The sum here, what is critical is this OR. Either is a sum, it is a number, or it is a number plus another sum. So the bottom line hopefully makes it clear. Notice here, and this is also something that I prefer better for an assignment. So this is actually a column, double column equal. So these are the symbols that are used to denote the production rules in our um, grammar to define what is the syntax of a natural number. So based on this syntax, one can design a program or one can design a machine that recognizes whether any given input is actually a valid sum. So we will not go in there, but as you read the production rules, you can read this also in a systematic way that defines an algorithm to recognize, to parse whether any given expression is following the rules of a sum. There are pictures. So there are the production rules that are given by the written rules, but you can also explain this as with a picture. So a sum is a number, which can be just a number, or it is a number followed by a sum and then followed by another number. So if you read this loop here, either you have the choice to leave or you have the choice to continue with a plus and then followed by another number. So what is a number? It is a digit. So what is a digit here? This is a circuit. Either you have one of the basic digits, so you can go through this and you can exit after one digit, or if you, so this is one digit, one circuit, and I had to do this rather cumbersome because my slides would occupy everything. But you can see I have here the first 5 digits and then the next 5 digits arranged here as just a simple circuit. And then I have the number, which is a sequence, a loop if you do, or if you go out. So these are syntax diagrams. So this defines a sum. As an exercise, you can think of what is a polynomial in X and actually define the syntax for a polynomial. That's an exercise. Okay, it is important, and at this point in the course, you may have encountered already many errors. So here is an error. Here are two different errors. And the question is it a syntax error or is it semantic error? So what is the context? So X is a variable, a name of a variable. And you want to cast the value, which could be an integer, you want to cast this into a float. So these slides are not the most recent, so Python has become a little bit more friendlier, and it will give you some hint for the error message at the bottom. It will actually ask if you have misspelled it. So this exercise has become a little bit easier with more recent versions of Python. A spelling mistake is an example of a syntax error. So the second error, although it is called name error, so we will see later on in the course that we can make our programs more robust, that we can actually capture these exceptions. But both errors are actually recognized or labeled by the Python interpreter as name errors. The second is a syntax error. Yes, the second error is a syntax error. The first one is actually a semantic error because I had not defined in the context of this statement the name X is indeed not defined. So you see, Python gives the same error message, but one is a syntax error, the other one is the syntax error. Syntax errors are just spelling errors, and if you are using the editor, the syntax error, the syntax aware editor in the Jupyter Lab environment, it should already warn you with colors that if you make a spelling mistake, that it captures this. So syntax errors are easier than semantic errors. And then there are the logical errors, which are even worse to detect. But for the purpose of this lecture, we distinguish between syntax errors and semantic errors. Okay, let's travel to Python. So we briefly encountered lists in the previous lectures. Lists correspond to loops, and it's often better to look at lists before you return to loops. You will discover that a lot of algorithms that exists on lists can be done with one method, with one statement. Rather than that, you have to write your own loop for this. Strings are actually sequences of characters. In a way, they are composite data types as well. So strings are kind of, I would say, hybrid. It's not entirely logical that Python treats them as elementary data types. A character is elementary. As we have seen with the ASCII character code, a character can be represented by a byte. A string is much longer than that. Here you see the loops in a list. So we can turn a string into a list of characters with one statement. We will call this we call this a list comprehension. So for every x in the string, which actually means for every x for every character in the string, for every letter in the string, hello here in this example, for every letter, we add it to the list. Lists, notice here it's important the brackets, whether you use square brackets or round brackets. So you can immediately recognize a tuple from a list by the beginning and the end. So we use round brackets. So tuples occur very frequently all the time with arguments of functions and methods. So I'm actually applying a constructor. Again, in the object-oriented language, I can turn a tuple into a list by using the list and then round brackets tuple, or I can do it in the other way around, turning here a tuple, a list into a tuple. The main difference between lists and strings is that lists can contain anything, not just characters. Lists can contain other lists. Lists can contain tuples. Tuples can contain lists. You can store, the main difference between tuples and lists is that the length of a tuple is always fixed. So you cannot change the length. You cannot append to a tuple. You can append to a list. We will see applications of tuples in the next part. All right. We have seen that with Python, we have variables that refer to objects. With lists, we can make an other intermediate step. So if we place a bracket around a number, we actually make a list with one element in there. So that's one way how to make a list. What you actually do is that you make another name for that object. So in the first assignment, X refers to the number 3 directly. The list L contains the element 3, and we can not directly get access to it. We have to access it through the index 0. So that's another name for the same number. So in some sense, when you create a list, you create a whole sequence of other names. And the names are all very same. So they are L0, L1, up to the L, the number of elements in the list. So this is an important picture to keep in mind. When we will defining functions, we can see that we can do very powerful things with lists that are arguments. of functions. We can share references. So here is a very simple calculation where we can change the content of a list by not explicitly referring to the list, but only indirectly. If we are assigning one list to another, we are essentially assigning references. When you assign variables to each other, if you have x equals 3, y equals x, then you are essentially assigning to y the variable 3, the value 3 again. If you do this with lists, you are just sharing the reference. And here you can see that you can change the value of what is inside the list L by changing the referenced copy K. So when you do the assignment, you change the list L as well. Sounds like a far-fetched trick. It's a very important tool as a programmer. You must know when to make a copy of a reference, which is very powerful. You don't have to make a physical copy of your data. But sometimes you want to make a physical copy of your data. You want to make a deep copy. As a programmer, you must be aware when you are doing the functional way of purely functional view of um, manipulating data, or whether you are manipulating data through references. Okay, I defined the formal notation of an integer number or a natural number. Do the same for a floating point number. Note that a floating point number also can be negative here. Perhaps an intermediate exercise is where you define the Backus-Nauer form of an integer number, which also has a plus or a minus in front of it. Python has the abstract syntax tree, a word that you will also recognize if you would look at the paper for the Turing Award lecture. We actually imported the abstract syntax tree in a previous lecture for the literal eval. You can look up the Backus-Nauer form of the Python language. There are operators to print rational numbers. So this is the formatting. Perhaps this exercise is no longer relevant. I should actually have changed it into use the formatting string. Okay, the last exercise is the indication of languages again, evaluation of expressions, the precedence rules. So there is the power, the exponentiation that allows to make large numbers. There is a difference between the two. Explain this. All right. I'm almost half an hour in, perhaps longer than I have should on this exercise or on this lecture. I had in mind to do the demonstration online, so I will use the Jupyter notebook to illustrate the introduction of the basic, we are actually not the um, composite data types. So there's one language which I forgot to mention, which is Lisp. Actually, Lisp should have been added next to Fortran. Lisp stands for list processing. So if we have lists, we can already write extremely powerful programs. And actually, that is the start. Strings, lists, and tuples. Or perhaps I will start with strings and lists. So if we strings are everything that we can represent. So if you like, we have seen the ASCII code. Everything that is a sequence of zeros and bits can be represented by a string. So we have the hello string. Um, so it's good practice to have every statement in one code cell. So this is a string. Everything is typed. So the str type. Str is the name of a type. It's also a way to take any object and turn it into a string. So we can turn a string into a list by a list comprehension. So saying that for every x in the string, I will list it. So that lists all the characters in a string. And list is just the type. Now, how do I go back? So I said that there is the string method. That would be another way to turn a string representation of a list, but it is not what I actually want. So I can join the characters in a string. The join is here done with the empty string. So the empty string is presented by just open the right quotes, close the right quotes. I can actually join with anything. So let me join with hyphenations or join with commas. So here you see the processing of strings. So I start with a simple string and I can put hyphens in there. There are methods on lists as well. Do help L to see everything. How do you reverse the elements in a string? So actually this was something that I did not want to do. I probably am distracted now. So how do I reverse the characters in the string? Well, I can reverse the elements in a string. So this is a method that actually changes the list. And now I can rebuild the string with the join. So as an exercise in loops, you can check whether every given string is the same string when you read it forwards or when you read it backwards. You can solve this problem with list processing. So you can make a very simple program now that prompts the user for a string, computes the reverse, so here hello versus Ole, and then compares the two strings with the equals equal sign. And that will print true or false whether the word is the same, if it can be read forwards or backwards. So you have the name Bob, B-O-B, whether you read it forwards or backwards, you have the same word. So this is called a palindrome. All right, this is still untitled, not very good practice of me. So I should say that this is the notebook that I make during the recording. So I'm talking a lot. If I prepare this, I write a lot. So this is in some sense very Spartan. No markdown cells to say to denote what I actually write. All right, we have the join. Is there opposite? So I had my string hello, the hyphenated one. How do I undo? Well, there is the split. Split will split on any symbol in the argument. So very convenient. So you can split any string on the characters and you will get um, a sequence on there. A sequence of the characters that are separated by any character that you gave as argument of the split. List processing, very powerful. So let me go into tuples. So tuples, I will make another header. One application of tuples is to swap arguments or swapping elements. How do I make a tuple? Well, I can make a tuple as I did on the slide. I can turn a list into a tuple. So here we have the tuple T. Sorry, I have the type. I want to indicate that T is a type. It's a tuple. I can turn any tuple into a list. So you cannot change the length of a tuple, which could be very frustrating and inconvenient. Well, what you do is you just turn your tuple into a list. You do something to it, and then you turn the added list again to a tuple. So there is always a way to do this. Now, what are tuples good for? So tuples are good for assignments, initialization. So if you have, oops, um, if you want to assign to A and B the values 1 and 2, then you can do this in one single statement. Good. What if you want to swap them? And this is important here. This is what I feel is one of the main applications in of tuples. And I will write that down. What if we want to assign to A the value of B and to B the value of A? What if we want to do this? Well, you may say, why do we want to do this? Well, there are applications for this. Swapping the elements. Now, if you think about this, if you were to do this without tuples, You would first, so here is the wrong way to do this. So I will assign to A the value of B, and then I will assign to B the value of A. That's the straightforward way. So now you see what happened. A became B, but then B became A. So they now have both the values A and B. The values too. Very bad. We have lost. Uh, so the way to do this, if you don't know tuples, is to work with the value C. You first save. The value of B in C, and then you override B to the value of A. And then you assign to A the value of C. And there are things that can go wrong with there. So the proper way to do this is via a tuple assignment. I have to redo it again now because if you run this script top, this notebook top to bottom, it will not work. So let me verify very carefully that A refers to 1, B refers to 2. Then I can do everything in one tuple assignment. I can say that um, A and B has to be B and A. So now you see that I have A equals 2 and B refers to 1. So this is an application of uh, tuples, tuple assignments. Okay, in composite data types, we can select and slice. So that's the next topic. So I will explain how indexing and slicing works. So I am making this Jupyter notebook interactively. I hope that it's also a little bit clear that I can do this very quickly, because as a Python programmer, these are things that I do not have to look up. So every programmer has familiarity with the main idioms of the language. So this is the first time that we are doing this. So you may have to look things up and look for more examples. So how do so I indicated that L naught on the slides is another way for the first element. So L naught is the first element indeed. L1 is the second element. And actually you can also say L negative 1. So that will give you the last element. So this is the indexing. So you can select individual elements from the list. So it is important to distinguish the elements that are in the list and the positions of the list. So we distinguish between the values in the list, so here the letters, and the positions of the values in the list starting from 0. So these are called the indices. So an index, go to your index finger. So this is how you address every single element in the list separately. It also, by the way, works for tuples. Tuples have the same indexing. We can slice. So if I want the elements starting at 1 and ending at 3, I can make this slice. So this gives me the L's. Notice it's not ending at L, it's ending at L minus 1. Because actually what you often may want to write is you want to write the length of L. So this goes all the way to the end. So the length of L is a function on the list L. It returns the number of elements, which is 5 in this case. Okay, indexing and slicing. So again, with processing of information, if you like, all the information is sequences of zeros and ones. We humans see sequences as strings. With lists, we can transform the strings into individual pieces, letters if we want, and you can manipulate these links. You can reshuffle them, resort them, make all kinds of sequences. So in a way, at a very basic level, if any program takes a sequence of bits on input, a string on input, and returns a string on output, with the list processing, manipulating lists, reshuffling them, adding elements, slicing, joining them, you can make essentially any combination of the given inputs. All right, I have 4 minutes left, and there was something that I left out for sure that I had prepared. Indexing and slicing, and then there is the demonstration of the sharing of the references. So there is the deep copy, and we have actually already seen how to make a deep copy in the first instruction. So you can do or the second instruction here. You can run this statement also instead of S. You can run that on any list. So you can make a deep copy, or at least a copy of the first layer of values if you run this for loop. There is also the deep copy module that will, in case of nested data structures, will actually make the deep copy. Okay, I will post the prepared Jupyter notebook that contains more documentation, a little bit more on what I have explained. But it should be clear that Python is very powerful, contains too many things to know all at once, but topics that we have covered today is something that should be familiar to every Python programmer. So the indexing and the slicing, for example, is something that you should not look up when you write your Python programs, when you are more experienced as a Python programmer. Okay, most of my lectures, most of my pre-recordings went over time. I do not want to do this now, so I will stop.